So yeah, let's talk about Verkle Trees. So this talk will mainly cover some introductory aspects of what Verkle Trees are and how they work, and basically how how do they fit in the roadmap of Ethereum in the next years. So a bit about me. I work at Polygon Labs as a blockchain protocol engineer. I am also an Ethereum protocol fellow. So currently I'm working on the in protocol proposer builder separation project. So yeah, if you want to discuss anything about that, feel free to reach out. Uh, yeah, and few different things. So okay, what's the outline? So before we move to the upgrade called Verkle Trees, I want to cover a bit introduction to the current state of Ethereum, right, which is Merkle trees. So Ethereum currently uses Merkle trees as its data structure. So like before everyone knows what the upgrade is, it's important to understand what the current state is, right? And we'll touch upon a bit of a domain called statelessness, because Merkle trees, uh, like with implementing Verkle trees, the end goal is to achieve this thing called statelessness, and then we'll see how the tree is structured and like some of the properties of the tree itself. Okay, so how many of you are aware of the Merkle tree which is used in Ethereum? Okay, and how many of you are aware of the Patricia component of the Merkle tree which is used? Okay. Yeah, so I've been talking with a couple of people here, and so there seem to be like few people who know how Merkle trees work, but they know it from a very simple data structural point of view. But the actual thing which is being used in Ethereum is quite different. So yeah, I hope this might give you a bit more clarity. Also, yeah, I plan to blabber some random words in between my talk. So if anyone after the talk tells me any three words which I blabbered, I'll give them some goodies, so stay away. Okay, so yeah, this is how the Ethereum state currently looks like. So basically, if you're aware, Ethereum is like a global state machine. So it processes transactions and updates this thing called a state, which is called the global state. What does the state contains? The state has all the account related data, so basically your balances, nonce and everything, and also your contract related data, which is the variables of your contract, the slots of your contract, and so on, right? And basically after every transaction, so let's say if I put a transaction of simple ether transfer, it updates this state which is shown below. So this is a simple example of a Merkle tree. This is not exactly how it's used, but just for sake of clarity. So you have this thing called leaf nodes, which is a common property of the tree. So all the data, all the actual data which has some value lies there. So let's say there are 4 accounts in Ethereum. They may be normal accounts, they may be smart contract accounts, and they lie in these leaves. And what you do is you hash them to get your parent node. So basically the value of every node is nothing but the hash of its child nodes. That's it. Simple as that. So over here, if you see there are accounts A1 and A2, so you get B1, which is hash of A1 and A2, and so on, you get B2. And similarly, you move up to get a single element until you have a single element. So that's called the Merkle root, or basically simply a root. And what Ethereum does is Ethereum puts this single value inside the block header. So you know that after a block has been processed, this is the exact value which everyone should arrive on, and this is how they come to a consensus that everyone should have this singular root present with them, right? But yeah, that's just the example. That's not how the actual tree looks like. The actual tree is okay. Yeah, the image is a bit blurry, but something like this. So sorry. Basically, what we saw was an example of a binary tree, a binary Merkle tree, but in actual it's like a hexary tree. So basically every node, every parent has 16 children. So instead of binary where you just had 2 children, there are now 16 nodes, and you have to hash all of them to get the value of any particular node. That's one thing. So that's one change, and the Patricia component. So what happens is that it's also a prefix tree. So a simple definition of prefix tree is that, let's say you have some hash xyz, so you move to, so you start reading data from the beginning, so you read x, you reach to a node, so that's the prefix. Now you read y, then you reach to a new node, which is the prefix. So the value at that point is basically the value of the key x, y, and you have the value there, right? So what Ethereum optimized this for is that there are a lot of nodes which might be empty, right? Because not all accounts have some data. There are a lot of accounts which haven't yet created. So there are a lot of contracts which haven't been deployed yet, or an external loan account. So what they do is they basically, so if there is if it reaches a path where there is only a single node at the very bottom, it compresses the whole path into a one node, so that you don't have to store these extra zeros in the 16 childrens which you have, and you can save a bit on your disk size and everything, right? So that's how the whole Verkle Trees tree works. Okay, coming to the second topic, which is like a building block for Verkle Trees, which is statelessness. So, right, why do you need statelessness in the first place? So it's very impractical for a normal home staker or a person with like a normal hardware to run these nodes, because basically they need high memory, and most importantly they need a very good disk, probably an SSD with a good disk IO, right? Because what they have to do is, like, on every transaction, on every block, they have to upgrade the state, and the state is very big, like probably in TVs, right, for Ethereum and for other networks as well. So what they have to do is they have to keep maintaining this state, they have to keep performing updates to this state, which is like slightly impractical for, it's basically resource intensive, it's not a simple operation, right? And because, I mean, there's like new activity going on Ethereum or other EVM chains, the storage will increase, like there's going to be a definite increase, there's no decrease in the storage, right? So what the current architecture is, it's also known as stateful architecture. Basically, if you want to reach to a state n+1, you need to have the previous state, which is state n, and then you have some transactions and you reach to a state n+1. You can't reach directly to state n+1 without any data whatsoever, right? So you need this. So basically it's like building up from Genesis to the tip of the chain, which is like 40-50 million blocks of Ethereum. So it's like you are building everything, you are keeping up everything to reach to this tip of the chain, right? And so Bankard is like an amazing researcher at Ethereum. He has written some more arguments to why it's important to go stateless. So you might want to give it a read. Yeah. So coming to statelessness. So why do you need statelessness, or what do you exactly mean, right? Basically, it's simple as it sounds. You don't need to have all the state or any of the state, right? In order to, come. Let's say in order to come to a point, or in order to take part in the consensus or the validation. Basically, if you want to download a block, you yourself should be able to validate it without any state whatsoever, right? So what's the current method? So let's say if I want to run it on my laptop, I don't want to keep this whole state. So now how do I trust? So what's the current method which I would have used to get some data? Let's say I want to get the balance and I don't want to keep the state. So I'll ask a full node that please give me the balance of this XYZ account, and they'll return me this the value. Now there's no trust in this because it's a P2P network. Nodes are not identified there's basically no identity for the nodes. They are anonymous. So you don't have any way to trust if the balance which is being responded with, basically the response which I'm getting is correct or not, right? So they choose not to trust them, and hence you can't have very much you can't have stateless clients because there's this trust assumption which comes into picture, right? So what's the next step? You add a witness to the block. Witness is basically a short proof that okay, this block contains these transitions, and so this is the block and this is the proof that these transitions are correct, and you yourself validate. So it's basically self-contained block or self-executable block that you don't need to have any historical data. With the data of the block itself, in some extra things, you can basically validate or verify that this is a correct block, right? So this is like the property of weak statelessness. So basically means that in order to propose a new block, you actually have to perform all the state transitions. So you need full state, but in order to validate, you actually don't need it. So it's not a necessity. So that's where the concept of weak statelessness comes in. So that's the first goal for Ethereum to reach there, and then there are certain future options which they might consider. Okay, just an example of a simple Merkle proof, right? So we talked about these witnesses. So now we are more narrowing down on these things which will lead us to Verkle trees. So yeah, this is how the current Merkle tree would look like. Just an example. So let's say this is a binary Merkle tree. So there are like each parent has 2 children and like it's 4 level deep. So let's say if the green one is something which I want the data for. So I want to prove that the result, this leaf 0110 exists in this tree. So now how do I prove it? So I have to generate this proof, right? So what will I do is that I'll give this additional element which is called sibling, which is shown in red. So red is associated with this green. So I already know green. I'll give this extra data called red, and I'll get the blue because it's just the hash, right? So now in order to move up the tree, I'll do the same process at every level. So I'll give the siblings at every level. So I'll give this another red, and I'll get the hash on the top. Similarly, it goes on. So yeah, it can be formulated. Basically, you need 4 hashes, right? But this is simple binary tree. What if we have a width 4 Merkle tree, which is like basically adding 2 more children to each parent, right? So you need now 3 additional elements at every level. So you need 3 additional siblings at every level, and that gives you 6 hashes, right? So basically, if you go to a hexary tree where you have 16 children, in order to prove one value, you have to provide 15 additional values at each level as you go up to the tree, right? So that's a bit of a problem. So enters Verkle trees. Yeah. So let's understand Verkle trees with a simple analogy. Full credits to Guillaume Ballet, who's like the lead developer from the Ethereum team. He showed this excellent example at one of the ECC talks. So basically consider that there is this map and there are like 4 pirates. The map has this way to a treasure, and what they do is they divide this map into 4 pieces. Each of them has their own piece, and they have the map shared with them. Okay. So now let's say the pirate one wants to opt out of this process and it wants to say that yeah, I'm willing to give this map to someone else. I'm willing to sell this map to someone else, to any pirate, right? So let's say someone comes to this pirate and buys this map. Now what's the guarantee that this map is correct? Like the pirate is not faking this map or not giving any false results, right? So simple. A Merkle proof analogy would be something like you provide the siblings, which is this map, this piece, and this piece. So you group them together to see if it like fits in the map. So you get this whole path reconstructed, and then you can then someone can verify that yeah, this is the correct piece, and I'll buy it. Can we do better? But so Verkle proofs is something like this, that you take out a very small piece from the between, and you then split it to 4 parts. So now if you want to prove it using a Verkle proof, you just need this middle part. So of course, like you might think that this is a very small part, but this is just an analogy. In practical usage, they are secured by cryptographic commitment, so that shouldn't be an issue. So basically, you match your piece with this, match your paper with this small piece, and you will easily be able to validate without needing any of the siblings out there, right? And you just did your work. You don't need the 2 pirates at all. Okay, and yeah, your work is done. So okay, so this is a very simple analogy to Verkle trees. So the name itself basically says that it's a combination of vector commitments and Merkle trees. So we'll come to what vector commitments are, but consider that it's similar to a hash function. So in normal Merkle trees we had hash, and now we are moving to this extra commitments called vector commitments. And it will basically lead to shorter witnesses in the Verkle tree. Okay, so what's a vector commitment? Going a bit technical. So let's say a vector, right? You read about vectors in math or physics, whatever. Basically, vector is basically list of elements. Let's say x1 to xn. So what you do is you have something known as a commitment, which is like a cryptographic commitment to this vector. Basically, a commitment can be simply understood as that I commit to these set of values, and here's the proof that I committed, right? So that's a short commitment value. And you have another concept called openings. So you have this whole vector and you have this commitment. Now I want to generate a short proof that in this vector, I want to generate a proof that at ith element, the value at ith element is whatever, v, let's say, right? So that's something known as opening. So what you provide is you provide the commitment, you provide the whole vector itself, you provide the index which is I, and you also provide the value which you want to prove. So opening CXIV is basically a proof that xi is equal to v. Basically, v is in the ith position of the whole vector. Simple as that. And an interesting point is this, like from a cryptography perspective, that this proof is extremely short. So it's like 32 bytes short, and it's like a constant size proof, right? So even though your vector is like extremely large and it contains like more than 1 million elements, your proof will still be of the same size. So which is very impressive from a compression point of view. So yeah, coming back to the same example, like the same tree example, that we wanted to prove this leaf 0, 1, 1, 0. So now earlier what we used to do was we used to provide all the siblings up to the root. But now what? So main thing over here is, as I said, like we replace the hash with the vector commitments. So the value which is in red, which is like the inner node 0, 1, which is the parent of these nodes, that contains the vector commitments. That does not contain the hash of the children, but it contains the vector commitments. And the vector here is basically the child element. So the leaf 0, 1, 0, 0, 2, 0, 1, 1, 1. That's it. Like all those 4 values below it, they are part of this commitment. And similarly, root contains the vector commitment for all these 4 inner nodes. That's it. So now let's say I want to prove this value leaf 0, 1, 1, 0. So I have these 2 proofs. So my proof, like the number of proofs are 2. But what I'll additionally need to show is that I need to show an open of 3, which means that this leaf belongs to the 3rd position of this vector commitment of this vector v. Right. So there's one opening. Then I also have to prove for the parent block that where I use opening of 2, which basically means inner 0, 1 is on the 2nd position of this root, right? So basically there are sequence of proofs which you need to give, but understand the optimization here is that you only need one proof at the height, right? At one level. You don't need the siblings and everything, so you get rid of, and you store basically a lot of space. Yeah, but as Vitalik says, this isn't even the final form, right? You can optimize further. How? So you can merge these proofs into one proof. Basically, let's say if you represent the state correctly, I won't go into much details of that, but 2 commitments or 2 openings can be clubbed into a single proof. So if 2 can be clubbed into 1, and n commitments or n openings can also be clubbed into 1. Correct? And so it's like a mathematical thing that if you merge the polynomial, if you merge the commitments of 2 polynomial, it basically gives you a single proof, which is the commitment of the sum of those 2 polynomials. So this way, if you represent the polynomials or the vectors correctly, you can combine everything into a short proof. So over here in this example, instead of giving 2 openings, you can only give just 1 opening. And if it's like, let's say 7 or 8 levels deep, you still can give represented in 132 byte value, which is super awesome. So what you need to do for this, like combining this proof, is that you need to prove a sequence of statements, right? So over here, I mean, just for an example, like we need to prove that node A is the child of root at position I1, then node B is child of node B. Okay, node B is child of some other node at position I2, and so on. And your final proof will be these commitments at one level. So there is one commitment in one level plus a common proof. That's it. So yeah, your proof size basically reduces by a large extent. What are the properties of a Verkle tree? So basically for an inclusion proof. So what do you mean by an inclusion proof is that you want to prove that this value xyz node belongs to this whole tree. So that's where the proof comes in. So if you want to give an inclusion proof, you don't need any siblings. So and you only need the path towards the leaf, right? So you need one proof per level. So now what this opens up doors for is that restructuring the tree. So currently the Verkle tree is structured in a way which is like quite a few levels deep, but because you don't need any siblings, you can make the tree much shallower, and you can make the number of, you can increase the number of leaves from 16 to like a higher number like 256, right? So this lets you have a very shallower and wider tree, and like the current decided length based on the cryptographic assumptions is that there will be 256 children for a single parent node, right? So this makes the proof short and efficient, of course, and basically lets the verifier who wants to, how do the verifier verifies? They can basically use this commitment to verify that this child node is actually at this position of this parent node, and so on. They know that this thing is actually included in the whole tree, and the prover is not faking it, right? And one of the main constraints is that for Verkle proofs, like the proofs are so weak that you can't propagate a proof in the network very simply, because the block time of Ethereum is 12 seconds. So you can't propagate everything in this 12 seconds to each of the participant of the network, right? But with Verkle proofs, what you can do is you can easily put it inside the block body or block header and propagate it, and anyone who doesn't even have a state can verify it. So a specific thing which they are planning to use is they initially started with using KCG commitments, but they are using currently something known as Peterson commitments with a single, and like the openings are basically a single point in an elliptical curve, right? So it's just 32 bytes. So some numbers from some of the experiments which I think Vitalik has mentioned in the EIP of the Verkle tree. So yeah, the cost for a Verkle tree, let's say assuming that you are accessing a single account, so for that the witness cost is like 3 KB. So for a 15 million gas block, like which is not even the full gas block, right? The total limit of Ethereum gas is 30 million, and like even if we fill the block half for an average case, it basically creates a witness of 18 MB, which is very huge and not possible for someone to transfer it with a block and keep up with the chain, because the block time is 12 seconds, right? With Verkle trees, the proof comes to 200 bytes, so per account. So witness size is like 1.2 MB, which is like significantly less. And technically, with some of the optimizations, there will be much more reductions because the thing is the way it's structured is that they are planning to group frequently accessed elements together. So for more number of accesses, you will still need same. You can still reuse those proofs, right? So it's much more less than 1.2 MB as well. And yeah, so this is how it's basically structured. I'm not sure if it's visible correctly, but basically they have this something known as stem tree. So it's again like it still remains a prefix tree. So even after all the hashes or all the commitments you do, you still have to follow the tree path up to a certain point. And there is this extension node which I talked about, where it like compresses the data of the childs below it. So that's a Peterson commitment of like of the 256 elements which lie below the extension node. Yeah. And even at like a granular level, the values which are stored at the leaf nodes are divided into two 16 bytes elements. So that's where this value lower and value upper comes into play. So they're grouped together, and hence there are two commitments, C1 and C2 for that. Yeah, benefits as we said. So it will enable stateless clients to Ethereum network. Basically, you can run a very lightweight node where you don't need to maintain any state at all whatsoever, and you can just verify a block directly. So basically, blocks are self-contained execution units and contains all the data. So let's say if you are a custom node operator and you are only interested in some specific transactions, or you only want to gather info of some specific things, you can do it, because you get a block, you see the contents of the block, you decide if I'm interested, I'll download the whole block, I'll get the Verkle proof, and I'll perform the transactions or do whatsoever I want. If I'm not interested, I'll just skip the block. And so you can do this selective sync mechanism. And of course, like, it enables more people or more normal stakers to join the network to validate. So it's of course like leads to more decentralization. And like there are like further roadmaps by Vitalik to like improve it using snarks. So currently these are just commitments, and like they don't necessarily need to be zero knowledge based. They can just be simple snarks, and the proving could be much improved in the later upgrades. And also, like, it helps a lot in some of the upcoming upgrades, like state expiry and sharding, because using Verkle Trees, what you can do is, like, because you have this strong cryptographic assumption or commitments, you can perform a lot of operations on the validator committee. So yeah, it's helpful in that way as well. Yeah, so like, just in case if you want to read anything about Verkle Tree, there is this huge link from Ethereum Foundation called Verkle.info, which has everything. Yeah, I mean every progress element of Verkle Trees. It's basically it's already implemented in Go Ethereum, and the other clients are catching up and also implementing in their way. And of course, like, the other talks by these guys are super awesome. Yeah, thank you. Please let me know if you have any questions or want to talk about more about it. We can surely discuss.
There has to be. It's okay. There has to, like, hashing is pretty efficient, right? So, okay, I do understand that this commitment gives proof, but that is generating it costly, or there has to be some catch.
Yeah, so definitely it's like quite not quite, but it's like, of course, more resource intensive as compared to computing normal hashes. But again, I mean, because updating a tree only requires you to update the parent nodes, so you are only touching a few values over the path. So of course the cost is higher, but the proving cost is significantly less. So that's the trade-off. Yeah.
And, so, in a 16 root Verkle tree, where you're computing, you said that you need 15 others, right? But we can hash the 15 others and provide just single hash as the, like, complement to a particular state, right, at the root. So
yeah, so I don't think so.
It's not possible.
Yeah. But yeah, a good question. I think it does individual level of hashing. That's why it's not possible.
Or some format in which it combines.
Yeah, some format in which. But yeah, interesting.
Hello. Yeah, my question is that why do we need IPA and multi-proofs along with the polynomial commitments? IPA is in a product argument.
Yeah. So IP is, as I mentioned, like in one of the slides. So because these openings basically they are openings for a polynomial, right? Like it's basically opening for a data vector. So it's like there's this whole amazing blog by Denkart which explains how IPS work. So where it mentions that you can basically have this different polynomials and you can generate a common proof which is addition, which is basically proof of a polynomial which is addition of all of these. So it's like combines everything into one, which is like sum of all polynomials. Yeah.
Hey, so my question is much more about the application side of this. Like Verkle Trees are awesome. I understand that the decentralization is more proven and all. So I come from like a Solana side of as well, where they have this thing called compressed NFTs, right? So do you think like Verkle proofs can also get compressed NFTs on Ethereum? Because the idea is very common. It's just that we store less data on chain. We need less computation units to like manipulate, so the even the transactions are quite smaller. And yeah, so like what do you think on the application side of view, what kind of new applications or what kind of new stuff can happen on Verkle Trees on Ethereum?
Yeah, I think so. Once they start posting these proofs inside a block, uh, applications can actually consume it to like access some sort of data and like also generate proofs on their own is what I think. Uh, yeah. Apart from that, I think like they are trying to build a lot of tooling around it. So it's still in early stage. I'm not pretty sure what changes. So it's definitely going to bring some changes for a contract developer or a Solidity developer. Yeah.
Makes sense. Thank you.
Yeah, any more questions?
Can you talk more about the state tree, the depth of it, and details about it?
Which
And
thing?
state tree, right? There's a
Yeah.
so that part. And the second question is it a part of 4844 EIP, which is going in Cancun?
No. So to answer the second question, no. It will be as a major upgrade called the Verge in Ethereum. So it's not going with Cancun for sure. Coming to the first part, I'm not pretty sure what's the size because it depends on the elements, number of elements which are present in the leaf. So like I don't have the current numbers of how like what's the length of the leaves of the Merkle Patricia tribe. So depending on that, like how they fit in, there'll be the whole tree will be constructed. So basically the transition plan is something like this, that we are going to use an overlay method where they'll have the Merkle tree and they'll also construct a Verkle tree parallelly. And once the Verkle tree is constructed, they'll discard the Merkle tree. Yeah, so it depends on that. And I think so a rough estimate would be I think 6 or 7 levels maybe. But yeah, not very sure.
So yeah, any more questions?
You guys.